In the real world, recursion is very useful. Recursion is, it's usually never, I say usually never because I hate absolutes. There's always an exception, it seems, which is an absolute, interestingly enough. Um, Usually never the only way to accomplish something with programming. It is, however, sometimes the best or most elegant way of accomplishing something. And one of those things that it is really awesome at doing is making sense out of complex data structures, like this nested list or the set of nested lists here. I can create a recursive algorithm, a recursive function that can take any nested list in any format with any number of lists and any number of members and explore that whole thing, every last bit of it, and make sense of it. And that's really tough to do without knowing the depth of how many times a list is nested or what the structure is or what the size is. That's a really difficult task to do without recursion. Is it possible? Yes, but recursion does it so much better. If I break this list down and take it apart into the nested pieces, it's a little easier to sort of see what's going on. So I've created these lists so that we can keep track of what's going on a little bit easier. This first list is the A list, right? It's got 1, 2, 3, 4, 5 items in that list. The first item, the third item, and the fifth item are names. The second and fourth are separate lists that contain B names. Okay, and then this list has 4 items, the second of which is a C list. And we could go on. I could create massive depth here in these things, or these could have each 1,000 members. It doesn't really matter. This algorithm will be able to explore and understand those lists no matter what the shape is. And that's part of the beauty of this, is because an algorithm like this that's recursive allows us to make sense of the world, or make sense of data, which is how computers make sense of the world. That's what we use for lots and lots of machine learning and lots of AI work, is algorithms that are able to be flexible in how they understand the world. So if I'm going to make sense of this, and the most simple way, of course, is to count the number of names here. Here's how the computer in a recursive function will traverse this list. Okay, so it's going to start here, and every time that function encounters something that is a list rather than a string, it's going to process that list. So it's going to take all these little side quests, so to speak. We've got the first one is a name, second one is a list. So it goes to this list. The first one is a name, the second one is a list. Now it goes to this list. First one is a name, second one is a name. The list is over. Once it reaches the end of a list, it goes back up and resumes what it was doing before. So it's another name, then it finishes this list, goes back up to the A list, a name, another list. And it's just going to keep doing that, and it will follow this list all the way through. So the logic, if we were to write this in pseudocode, says for each item in the list, if it's a single item, then count it. Otherwise, process it like a list. When we mean process it like a list, we mean use recursion.